Okay, good. All right, good. Can you hear me now? Someone thumbs up, good. Okay, yes, so this will be the last lecture. It's hoped that it won't take the entire hour and a half, and we'll have some time for general Q&A. As usual, if there's questions about the topics I'm talking about, definitely don't wait till the end. Just jump in and stop me, and we'll try to get them sorted out during the lecture. Okay, so just to remind you, these were the 4 sections that we have been discussing. First was about the motivation for WIMPs. Second was about a specific example of WIMPs and supersymmetry. And we found that neutralinos emerge beautifully in this context where supersymmetry explains why the strong coupling is stronger than the weak coupling is stronger than the electromagnetic coupling, explains why electroweak symmetry is broken, explains why the top mass is 174 GeV. It also kind of explains why the lightest superpartner is the neutralino, or at least neutral. And then that we could explore all sorts of interesting consequences in particular regions where you get the right relic density. And then I talked briefly about WIMP detection, direct detection, indirect detection, and collider searches are the 3 big ones. And this was done in a pretty sketchy, fast way, partially because of time, but also partially because you have dedicated lectures for these in the coming week. And so the organizers have very nicely organized this whole thing. And so I'll leave the details of these to them. So today we're just left with this 4th one, which I actually consider one of the most interesting. And this is WIMP variations, I'm calling it. And this is variations away from the standard WIMP scenario. What do I mean by variations? I mean things that still preserve the WIMP miracle. Okay, so that, as I've been trying to emphasize, is really sort of the key interesting motivation about WIMPs that sets them apart from everything else, basically. Sterile neutrinos, axions, where you can get the right relic density, but it's kind of tuned to be there. Whereas WIMPs, we have some reason why the relic density is what it is. So we want to preserve that. And that's why it's a WIMP variation, not just random other models of dark matter. But they're variations that are very interesting, not just little tweaks, because they do drastically different things. They can, for example, completely eliminate one category of searches from being interesting, for example. Or they can suggest new signals of dark matter. In particular, they can suggest that the cold dark matter is not at all cold collisionless dark matter. And so in some cases, they can sort of suggest that the WIMPs aren't even 100 GeV. These WIMP-like things are different from the mass scale that we thought we were stuck with. And so this is what's selected out these 4 particular examples. And so I'm going to go through each of them, giving you basically the setup, how it differs from the normal WIMP setup, and some of the basic, very interesting, qualitatively different implications for detection. Okay, so I hope that's clear. That's the goal here. Now let me scroll forward to get down to that section. Okay, so here's the sort of graphical representation of what I just said. The WIMP paradigm has spawned many spin-offs that preserve the WIMP miracle to some extent, but have vastly different implications for particle physics and astrophysics. This is the by now famous diagram of a bunch of different dark matter candidates from Tim Tate. And there are a whole variety. Some large chunk up here are supersymmetric, so I've already kind of discussed those. But then there are others, and so I'm basically picking out of these other things, those that are sort of preserving the WIMP miracle. Okay. So let's start with inelastic dark matter. So this is motivated by DAMA, which is a signal in direct detection, which I didn't really get to talk about as much as I wanted to last time. But essentially, it's a signal using a sodium iodide detector, which has an experiment which has seen claimed a signal for dark matter for over 20 years now. And for a long time, it was interesting because we had no other detectors that were identical in terms of being sodium iodide to test the DAMA signal. And so we were comparing DAMA with CDMS, which is germanium, or DAMA with xenon, which is of course xenon. And so there was a little industry of theorists looking for ways to reconcile the null results from other experiments with the seemingly positive results from DAMA. Just as an aside, I'd say that right now, there are experiments that have finally, after 25 years, tried to duplicate DAMA using exactly the same target material. They haven't seen a signal, which provides a model-independent, I guess you could call it a refutation of the dark matter, of the DAMA dark matter signal. But those are still going on at the moment. Anyway, whatever its fate, DAMA has been an incredibly fertile driver for new ideas in dark matter. And this is probably the first and most prominent one. So inelastic dark matter, it grew out of considerations of another SUSY WIMP particle, the messenger or neutrino, okay? I showed you before, we had a number of dark matter candidates in SUSY that were neutral. There was neutralinos, which we discussed at length. There was neutrinos, which I told you were ruled out. And then there were gravitinos. And we'll talk about gravitinos in a little bit. But neutrinos are ruled out, and effectively, those were the first inelastic dark matter candidates. And so there were papers from Hahn and Hempling and Hall, Murray, and Murayama. And then Tucker Smith and Neil Weiner really sort of made a big deal about this. And this is sort of viewed as sort of the classic beginning of a lot of activity in inelastic dark matter. So what is the story? The story is extremely simple, okay? It's an amazing how one can make little tiny modifications to your dark matter stereo and change the implications drastically. So assume that there are not just one, but two WIMP-like particles in your theory. Okay, we'll call them X and Y. And what do I mean WIMP-like? I mean, they have masses around 100 GeV, and they, weakly interact. They don't have other couplings. But in addition to that, assume they only have off-diagonal couplings to the standard model. So you could imagine you have XX standard model couplings, but we're going to assume those are 0. YY are also 0. The only way they interact are off-diagonally through XY couplings to the standard model. Okay, and this can be arranged in a number of ways, and these authors talk about them. It's not as crazy as you might think. Now, suppose that, as I said, these are 100 GeV, but their splitting is very small, like about an MeV. Okay, so there's some symmetry that keeps them very degenerate, but then there's some breaking of that symmetry, which splits them by some 10 to the -5 fractional splitting. What does this mean? Well, in the early universe, and particularly at freeze out, this is completely tiny, right? This is a MeV splitting. We know that for 100 GeV dark matter, it freezes out at about 5 GeV. And so no one cares about MeV splittings when you're talking about 5 GeV temperatures, okay? So this is essentially negligible. And so X and Y just freeze out as they usually would with this kind of a coupling, okay? So then you get some number of X's, some number of Y's. Eventually, because the Y's are slightly heavier, okay, given all the time that elapses between freeze out and now, the Y's will decay to X's. And then so you get all that reluctancy of X's and Y's poured into X's. And now you have X as a dark matter. And if X is 100 GeV, you've got all the reasons you think to have the right reluctancy because it's the WIMP miracle. But now, remember, now the velocity is not a third, it's 10 to the -3. And as I emphasized before, you can get a lot of mileage out of this difference. So once the velocity is 10 to the -3, all of a sudden, this mass splitting becomes important because if the mass is 100 GeV, velocity is 10 to the -3, kinetic energy is 100 keV, which is now small compared to the MeV. In particular, let's think of how you would like to detect this in direct detection. So we would have like X, typically you'd have X scattering off of like, down here, there's some corks or something, right? And so time goes this way. And so that would be elastic scattering. X goes in, X goes out, cork goes in, cork goes out. Clearly, that's not possible because there's a 0 here. But you'd say, well, okay, fine, that one's gone. But how about this? X scatters and makes a Y. It's just a little bit inelastic because the Y is slightly heavier, but we could do that. Well, no, you can't, because although this is allowed, this is not allowed by energy, because you would need an extra MeV to make the rest mass of the Y, and all you have is 100 keV kinetic energy. So we would call that upscattering, scattering of X into a heavier state Y. And the point is that given these parameters, there's just no energy to upscatter. So basically, you've just killed off all of direct detection without changing a single thing about the lamp miracle. You also do damage to indirect detection, because remember, indirect detection usually is XX annihilation to the standard model. And if you don't have this diagonal element, you can't do that either. And so you also basically suppressed all indirect signals as well. And so, this is a great scenario for collider physicists, because they are then the only game in town. You just eliminated the entire categories of direct and indirect detection. Okay, so that is an interesting other scenario. I should mention, going back to the original motivation, if the delta is not 1 MeV, but 100 keV, it turns out that of course, is right in the range of what kinetic energies are available. And it turns out you can then do very fine tuning, which basically suppresses the scattering off of germanium. CDMS was one of the leading constraints at the time, and preserves the scattering off of iodine, which is what DAMA has in it. And so then you could reconcile DAMA with these other null results. Okay, and so that was really the motivation of Smith and Weiner. But nowadays, this motivation is probably even more prominent, where you just eliminate the entire direct detection field. Okay, any questions about this first variation?
Yeah. So when we suppress this germanium and keep the scattering off of iodine, I guess this has to do with the mass difference between germanium and iodine?
Yes, that's right. So it's playing on very specific kinematics. And it turns out that, let's see, I guess germanium has a higher atomic mass than iodine, and just that kinematic difference changes sort of the kinematics of your, it's basically like billiard ball collisions, and so you can just do the analysis in sort of first year physics, energy momentum conservation, and you can see that is what it's playing off of. Good. Any other questions?
Any other questions? All right, I think everybody's happy, so oh, they're in the chat.
Sorry.
Oh, go ahead. Yeah, sorry.
So the scattering is suppressed on germanium, but it's okay for iodine, and xenon is just next to iodine. So what happens for xenon?
So at the time that this first paper was written, xenon wasn't even in the game. It's an extremely interesting story in direct detection. For years, cryogenic detectors like CDMS and DAMA were sort of the leading experiment. And then very suddenly in the mid 2000s, and I had a front seat for this through various review panels and stuff, the liquid noble gases took off. And so at the time that they wrote this paper, there wasn't a lot of discussion of xenon, wasn't any really. Now if we go to it, we can see basically it's pretty much impossible to reconcile DAMA with CDMS and xenon, even using things like this. And one has to, well, it's extremely difficult in any way to reconcile Dhamma with these other ones now, given how strong they've become.
Yeah.
Yeah, so I'm not sure I understood why you cannot, like, say, recoil a nucleus with this X sort of ground state.
Okay, so this usual signal is elastic scattering. X quark, say, goes to X quark. And that's ruled out because there's no XX standard model couplings, right? So then one goes to the inelastic possibility where you have an X coming in and a Y going out, but the available energy is just the kinetic energy of the X, because the Y is the X mass plus a little bit more. And that plus a little bit more, if it's an MeV or bigger, means that you don't have enough energy in the system to create a Y, even if it were, say, at rest. And so basically it's just energetics. There's not enough incoming energy to create the final states you would need, given that this is the only coupling available. Does that make it more clear, or is there
Sorry,
some
I
other?
was missing the fact that there is no coupling.
Okay. Okay, very good. So then I hope it's clear. Yeah, so these X's, these red X's mean that they're just zero. They're not allowed. And then this is the only one that is allowed. But as I say, the energy considerations make this irrelevant also for direct detection. Okay, I think we can go on then. So the next one is yet another Dhamma inspired idea, which was actually done with Jason Kumar and Danny Marfati and David Sanford a number of years ago. And this is called isospin violating dark matter. So isospin, of course, has different meanings in particle physics. In this case, what I mean is the symmetry between protons and neutrons. So recall that dark matter scattering off of nuclei has this form, okay? So you have a number of protons, Z, in your nucleus. You have a number of neutrons, A minus Z, atomic mass minus atomic number. And they each have some coupling. Protons coupled to the dark matter, neutrons coupled to the dark matter. And those are parametrized by these Fs. And so we typically assume Fn equals Fp. And then, of course, this collapses down so that this whole thing is proportional to A squared. And I mentioned this previously. Basically, in all the plots you ever see comparing different dark matter direct detection experiments, this is the assumption. And it's all hardwired into the plot. And so they will plot things like the cross-section off of protons, but nobody, of course, has a detector that's made out of hydrogen. And so what's done is you take the, say, result from xenon, and then you assume that sigma A goes as A squared times something, and then you factor out that A squared, find out what it would be for hydrogen, for a proton detector. Okay. There's no, however, no model independent reason that Fn and Fp are equal. In fact, they're not. I mean, there's no, strictly speaking, they're just simply not. So for example, if you have supersymmetry, some of the diagrams that mediate the Fn and Fp are, of course, everything's at the quark level. And it depends on where the up squark mass is lighter or heavier than the down squark mass. The only way they would be equal is if those masses were exactly equal, and they never are. And so at a fine detail, this equivalence is basically always violated. Now, typically, in some cases, approximately true, but if you're trying to deal with experimental data where you have a real Dhamma signal and a real xenon constraint, it's worth relaxing all sorts of theoretical prejudices and ask what happens if they're not equal. And there are theories we can cook up where, for example, Fn is 0. That's very easy. You have like a dark photon mediated thing. Dark photons, like photons, only a couple of charged things. The neutron is not charged, and so that just eliminates this one. And you could cook up other ones where even they have the opposite sign. Okay, so basically, isospin violating dark matter is this framework where you just simply relax the assumption that Fn equals Fp when you introduce one new parameter, which is their ratio. And what you find is, I guess in some sense, not surprising. If you consider Fn and Fp completely arbitrary relative to each other, you can do funny things. You can basically make the protons cancel the neutrons in terms of this amplitude. And as I say, because you just see a nucleus, we don't scatter off of protons and then scatter off of neutrons and add the scattering cross sections together. You scatter off of the whole nucleus. So you have to add in the amplitude, not in the cross section, and you can get this destructive interference. Okay, so here is a plot where we vary Fn over Fp, okay, in some particular region, from -1 in the center here to -1.5, -0.5. And this thing that's plotted here is defined very carefully, but basically it's how much worse you are actually doing than what you think you're doing when you assume everything just scales as a squared. Okay, and there are various elements here. So for example, let's take a simple one, germanium. Well, that's not that simple. Which one? Well, okay. Xenon is, of course, one of the most critical ones. What you see is that for xenon, as you get to this particular value of -0.7, you can basically eliminate the signal by a factor of about 10 to the -4. Because you basically are in a state where the proton contribution exactly cancels the neutron contribution, given the number of protons and neutrons in xenon. And other ones, will have also these massive dips. Like here's an interesting one. Sodium goes all the way basically to 0. The only reason xenon doesn't go to 0 is because there's actually several isotopes in a xenon detector. And so you can't kill all of them off at the same time. But the point is that, that's a drastic difference. Even for sort of normal models, you can eliminate the signals by factors of 100 without much tuning at all. And so at one time, and this was the original motivation, you could find that you could decouple xenon and all other leading constraints and keep the sodium high. And gamma is sodium iodide, and so you could keep the sodium in here. And so you could reconcile gamma with this sort of framework. Nowadays, the xenon constraints are so tight, and because there are several isotopes in there, you can't actually eliminate all of xenon all at once. So, xenon is an amazing material for so many reasons, but this is one minor reason, which is that xenon has several isotopes in it. You can't actually reconcile xenon with gamma anymore. But the lesson we get from this is, you should take comparisons across different target materials with a large grain of salt, because there's always this caveat that something was assumed about the particle physics. The model dependence is there. And if you break that model assumption, things can change relative to each other by very large amounts. And so, another thing is that if you ever find yourself deciding on whether certain experiments should be built or not, there's some value in having a diverse program and not just having every detector be made of xenon. A few made of argon might be a good idea, for example. Okay, that's it for that. Any questions?
I don't quite understand this destructive interference thing that's going on. Could you explain that again, please?
Well, so it's just seen in here. So there's some coupling to protons, and then you multiply it by the number of protons. And there's some coupling to neutrons, you multiply it by the number of neutrons. Z and A minus Z are of course positive, but FP and FN could be opposite in sign. So this could be, 1, and this could be minus 0.5 or something like that. And in that case, this thing is a destructive interference, right? These two terms have opposite sign in the amplitude. So when you square them for the cross section, you get destructive interference.
So I guess I understand that part. Maybe what I'm confused about, I think, is like, let's say Fn were negative. What would that mean in terms of its coupling to the dark matter? Does that mean it has some kind of like negative coupling?
Yeah, that's right. So it's just like, for example, up quarks have positive couplings to photons because they have charge 2/3, and down quarks have negative couplings because they have charge minus 1/3. There's nothing wrong with having a negative coupling, right? Of course, in the end of the day, when you compute anything observable, like a cross section, that can't be negative, but that's fine. You just take the absolute value squared and the magnitude squared, and everything becomes positive again. But it's just exactly like in the photon case, you can have destructive interference with some negative valued couplings, right?
Okay, thank you.
Other questions? Oh, yeah.
Yeah, so can you explain again what we are seeing in this plot? Why the x-axis is only taking into account the negative value?
Okay, so this plot, there's only negative values here because I'm trying to show the region where the effect is maximal, where there's the biggest effect. And of course, that's when you get nearly complete cancellation between the protons and the neutrons. And depending on your particular nucleus, that effect occurs at, say, -1 if you have a nucleus that has the same number of protons as neutrons, or -0.7 if you've got 2/3 neutrons, or 2/3 protons and 2/3 neutrons and 1/3 proton, something like that, right? And so this plot is designed to sort of highlight the region of maximal effect. In the notes I sent you, there's also the plot, I think, for a much larger range of Fn and Fp. And so you see a region where the effect is maybe of order of magnitude, but nothing as strong as this 10⁴ suppression. But yeah, take a look at the notes if you want to see the broader one.
Sorry. Yeah.
Okay, yes, thank you.
Yeah, Max, go.
I hope I didn't miss this, but I guess I'm wondering what caps me at 10⁻⁴ for xenon, for example. I guess there would be some Fn and Fp that would allow me to get all the way to 0 if I wanted to.
So, okay, yes, I went over this quickly, but this is what I was referring to by the fact that xenon has multiple isotopes in the detector. So I can't remember exactly. Somebody there who actually works on one of these detectors probably knows better. But of course, we did this very carefully when we did the study. But just to give some numbers, xenon has like an isotope that's 136, but also a little bit of 138 and a little bit of 139, something like that. That means the proton to neutron ratio isn't fixed in that detector. So there's some Fn over Fp that can completely eliminate the signal for xenon 136, but it doesn't completely eliminate the signal for xenon 139. Or you can pick an Fn over Fp that kills off 139, but it won't completely eliminate 136. And so just because that detector has in it multiple isotopes with different number of neutrons, you can't actually make this go to 0. And so it bottoms out here. And that's exactly the reason that you can't make the xenon results consistent with gamma anymore, because there's just no way to kill off the xenon result completely. You can eliminate it by a factor of 10⁴, which you would think is an incredible suppression, and of course, extremely irritating to do to the experimentalist who worked for years to get this thing to be a large 3-ton detector. But the point is they've done it so well that even when you eliminate the xenon signal by suppress it by 10⁴, it's still stronger than the gamma claimed bound or claimed signal. And so xenon still eliminates gamma in this framework nowadays. There's a question in the chat
Yeah.
about
What values of the ratio Fn, Fp would you say are motivated by UV completions of the EST description, or can we vary these freely?
so pretty much you can vary this freely. There are some particular interesting values where, like as I mentioned, for example, Fn equals 0 is the completely, you can do this with dark photons. But basically, once you put in some new interaction, which is sort of dark photon-like, you can basically adjust this thing around. And so, I guess the viewpoint taken with this work is that we as theorists have multiple theoretical biases, but they all crumble in the face of actual real experimental data. And so the idea was, let's try to peel away the theoretical assumptions and just let this thing be a free parameter and see what the data are telling us. Could it be actually telling us that we're in some region where Dama really does see a signal and is consistent with everybody else. But so the bottom line is, I would think we should take it as a free parameter, but within 30 minutes, you could cook up a model that realizes whatever parameters you want. It's not hard at all.
Are there any questions in the lecture hall? So there is one more question in the chat. So Catherine, you can just unmute yourself and ask, or I can read it.
Yeah, can you hear me?
Yes, please go ahead.
Yeah, I was just wondering, because here you of course talked about the implications of isospin violating dark matter on direct detection, but would there also be any implication on indirect detection, for example, or also to collider searches?
Yeah, so no, I don't think so. This is relying very specifically on scatterings off of nuclei. And in indirect detection and colliders, you don't have that. Maybe in some fixed target experiment, there would be an implication. But for colliders, just TP colliders or E plus E minus colliders, I don't think there's any implication. And so this is kind of, the theme that's running through here. These little model tweaks, you can do things, you keep the Wimp miracle. I mean, I didn't say this explicitly, but everything here doesn't disturb the Wimp miracle at all. And that's annihilation also, just like indirect detection. And you can keep even, indirect detection signals and keep collider signals, but vastly distort certain direct detection signals. And so that's the theme here, that you don't have to throw away the entire thing, but you can throw away pieces with very minor modifications to the models.
All right, thank you.
Yep, thank you. All right, so I think we can then go on to the third of 4. Okay, so this is the one where we're going to discuss then, in some sense, the last of the neutral SUSY particles, the gravitino. And so the gravitino, actually, as I mentioned, it's very interesting, actually. The gravitino was actually the first supersymmetric dark matter candidate discussed ever, before neutralinos by about a year or 2. Since then, it's had a lot of attention and a little attention, up and down. A lot of times it's just a completely ignored supersymmetric particle, but that's completely unjustified because there is a gravitino basically in every supersymmetric model. So let me first explain, why you can ignore it and then why you shouldn't, okay? So in supersymmetric models, there's yet another neutral particle called the gravitino. It has a spin 3/2 because its partner is the graviton, which is spin 2. So that's a little weird, but you can kind of think of it as a fermion, okay? I mean, it is a fermion, but you can think of it as just your normal fermions, which are mostly spin 1/2. Its mass can be anything, though, from an EV to a PEV. And this is true even in models where you keep the squarks and the leptons at, say, the 100 GeV TeV scale. Okay, so the gravitino mass is governed by other parameters that can vary quite a bit. The thing that is universal though is that its couplings are typically super weak. And I'm using this for those of you who do know some history of particle physics in the language that Lincoln Wolfenstein talked about decades ago, but basically it means weaker than weak, okay? So it's extremely weakly coupled, and that's, you know, maybe no surprise because after all, it's the partner of the graviton. And the graviton's mediating gravity, and gravity is extremely weak. And so gravitinos kind of get that same weak interaction because of their partnership with the graviton. Okay, so first, why is it that you can basically ignore the gravitinos in many studies? The gravitino is not the LSP. Let's think about, let's say at a collider, okay? So if it's not the LSP, we have a bunch of supersymmetric standard model particles here. We have the LSP, the lightest supersymmetric particle here, and the gravitino is not the LSP, so it's hanging out somewhere over here in the spectrum. It's extremely weakly interacting, so you never make it at a collider. You make squarks and gluinos and leptons and things. Then they decay down, but they will never decay here because that branching ratio is effectively 0 because that coupling is so small. So 100% of the time, all these things do is they cascade decay, boom, they end up with the LSP. And the fact that the gravitino is over here is just completely irrelevant. It's just sort of an innocent bystander to this whole business going on over here. And so for that reason, you could just ignore gravitinos in, say, collider studies, but also you can see that you can ignore them, you know, in WIMP freeze out, which is taking place over here too, and you know, direct detection of neutralinos and things like that, right? That's the assumption in most of the literature. The reason you shouldn't ignore them, however, is that, of course, the gravitino doesn't have to be not the LSP. It could be the LSP. It's got a mass that goes from EV to PEV. And so, you know, you could have a MEV gravitino or a 10 GeV gravitino, in which case it would definitely be the lightest superspectric particle. Then over on the standard model superpartner side, you've got a whole bunch of particles, but one of them is the NLSP, the next to lightest superspectric particle. And so what'll happen is, you know, you make a squark gluino over here, cascade, decay, eventually end up with this thing. Maybe it's a neutralino, maybe it's a Stau, who knows? But eventually, this guy will decay to the gravitino because there are no other choices. And at the same time, this is an open decay allowed by every symmetry and allowed by energy. And so then all of a sudden, the gravitino comes into the picture because every single event where you ever made one of these ends up with a gravitino. And you know, this became more and more prominent in the mid-90s with the discussion of what are called gauge-mediated supersymmetry models, where this is exactly the ordering of masses that's realized. And these people started off a whole new industry of thinking about gravitino phenomenology. So what does this have to do with cosmology and dark matter? Well, possibly a lot, because what can happen is the following. Let's say that the WIMPs and super WIMP masses are similar. So there's a whole class of supersymmetry theories, but they're not vastly disparate. So maybe the WIMP is, you know, 300 GeV, and the super WIMP, this gravitino, is 100 GeV. What happens then? Well, first you would freeze out. And as I say, when you freeze out, the gravitino, the super WIMP, has no relevance. So you just freeze out. But then eventually the WIMPs realize that they're not the stable super partner they once thought they were. They actually have an option, which is to decay to the gravitino. And eventually they will do that. And if you put in typical supergravity parameters, you find that the WIMP decays with a timescale like 1,000 to 1,000,000 seconds. Totally bizarre, but out pops is very normal time unit for humans, something like, you know, a week. So the WIMP freezes out after a nanosecond, sits around in the universe. the universe gets colder and bigger, and then a week later, it decays. Or maybe it's a month, half a year, whatever. It decays, and all of a sudden then the WIMP abundance drops because they're all decaying away, and you get this super WIMP abundance that then grows. And if you arrange things so that the WIMP has the WIMP miracle, and then it decays to a fairly degenerate super WIMP, then the super WIMP gets the right relic density. And so you can end up with a scenario where you have every reason to believe that the dark matter has the right relic density, but it's now in the form of super WIMPs or gravitinos and not neutralinos anymore. And this was a scenario proposed by me with Arvind Rajaraman and Fumihiro Takayama several years ago. Okay, so what does this do? Well, first thing it does is it wipes out all of direct detection and indirect detection, because what you're left with is a dark matter particle that is, in some sense, only gravitationally interacting, right? It's the gravitino. And so you can calculate its scattering rate in detectors, and it's 0. You can calculate how much it annihilates now, and it's 0. So, you just can't see this in direct detection or indirect detection. So in that sense, it's a complete nightmare. It's a terrible scenario. But there's a whole bunch of interesting astrophysical implications. So one thing is that super WIMPs are produced in these late decays, like after a week or a month or a year. That's maybe not late to a cosmologist, not late compared to a billion years, but it's super late compared to typical particle physics scales, 10 to the minus 25 seconds or something. So they're produced in late decays with large velocity, because you had WIMPs basically thinking they were the dark matter, and then each one just basically falls apart into a super WIMP and say a photon or something. Okay, so you had like a neutralino, which decays to a gravitino and a photon, and the gravitino is now going at 0.5 the speed of light or something after a week. Okay, this is a huge difference from the standard scenario. Standard scenario is WIMPs freeze out with a velocity of 0.3. Then they slow down. And actually, this came up last lecture. So one thing you have to understand is that WIMPs slow down just because of the expansion of the universe. As you know, photons redshift, they lose energy. Massive particles, their momentum also redshifts. And so basically, fast particles just slow down because of the expansion of the universe. And you can actually find out that the typical WIMP will slow down to walking speeds, like a meter per second, somewhere in the universe's history. Then when structure forms and galaxies come back into action, then it speeds them back up and gets them back up to 10 to the minus 3c. But yeah, when you're thinking about the velocities of dark matter, the interesting question isn't how did they get so slow, but how did they get so fast? Because they actually were going almost at rest at some point in the universe's history. Okay. Anyway, the point is that by a week, the standard WIMP is going extremely slowly. It's at rest, it's forming gravitational wells, sort of that kind of thing. All of a sudden, now we disrupt that picture by sending off these super WIMPs at almost relativistic speeds. And that just basically destroys all the sort of clumping that was about to begin. And so what that does is it suppresses small scale structure. And then you realize that these super WIMPs are doing the exact same thing that you think of hot dark matter or warm dark matter doing. They basically have large velocities late enough, so they're not very good at seeding structure formation. And so here's a plot from Manoj Kapling-Hat where you had, this is the transfer function as a function of k, this wave number. I think probably this was discussed in Anne's lectures, but there's some power spectrum here for cold dark matter. And as an example, Xiao neutrinos, which are the famous warm dark matter candidate, they kill power at small scales, which might actually be good given various problems like cuspy halo, or not enough sun halos, too big to fail, things like that. Super WIMPs do the exact same thing. They kill power at small scales. And so what I'm saying here is that this is a scenario where you just tweak the WIMP scenario just slightly. You make this gravitino not heavier than the neutralino, but slightly lighter. And all of a sudden, you don't have cold dark matter. You have warm dark matter, but with the exact same motivations. Comes out of supersymmetry, comes out of some weak scale theory, has the right relic density because of the WIMP empirical, but vastly different astrophysical implications. And there's also implications for BBN and CMB, because let's say you had a neutralino, which decayed to this gravitino and a photon. You're now dumping into the universe a large population of extremely high energy photons. What do those things do? Well, this happens, say, after a week. At a second, we establish this beautiful thing with BBN. And so, you're putting in photons that can destroy light elements. So you can disturb BBN. You can also do what are called CMB mu distortions, and slightly distort the beautiful black body nature of the CMB spectrum. And that can be seen too. So I won't go into detail, but this slide basically talks about BBN. Obviously, you can't really mess up BBN because that would be bad. BBN is a great success of cosmology, but you can have regions of parameter space where you don't disturb BBN significantly. And even more interestingly, have regions where you actually fix the lithium problem. As you may know, BBN is a great success with this slight fly in the ointment of lithium-7 and maybe lithium-6, which basically are too low. And it's possible that the photons that come into the universe can destroy lithium-7 and make it beautifully aligned with the observations in some scenario like this. So it might actually be good. And just to say the last thing, there are these mu distortions from on the CMB. So this is this beautiful Planckian black body spectrum. As you've heard, probably, this is the most perfect black body we've ever seen. But if we probe tighter and tighter, maybe we'll find that it's not quite black body, that there's some mu distortion, which is given by this parameter here. And this scenario actually can make mu distortions. So it'd be very interesting to probe those. There's a whole story about this. This mu parameter hasn't been constrained more tightly than the original Kobe data 25 years ago. It's a complete embarrassment to the CMB community that this has made no improvement for 25 years. And there are interesting ideas of improving this bound by, say, 3 or 4 orders of magnitude. And that would be a great idea in terms of probing scenarios like this. Okay, so that concludes this super WIMP story. Well, almost. Are there any questions?
Can you repeat why the WIMP is stable for approximately a week and then it suddenly starts producing these super WIMPs? I mean, why doesn't it start decaying earlier, right after freeze out?
So the WIMP has a lifetime of like a month. And you can find that out because if you just ask, what does a 100 GeV particle that decays through a Planck suppressed operator, basically through gravity, what is its lifetime? And the answer is about a month. So that's the lifetime. Of course, the WIMPs do decay at the beginning, but not very many, right? So on a log scale, they kind of have this this look where most of them decay at the lifetime, which is a month. But of course, you're right. Some of them do decay up here. It's just a very negligible amount for the first, Now, if it's a month, then the number that decay in a second is, 1 second divided by 1 month. So it's a very small number decay at the beginning. But after you go several lifetimes, of course, they've almost all decayed. And so there's no more by the end here. So it's a So, it's a colloquial way of speaking that they all decay at a month. What that really means is they have, gradual decays with a decay constant that's a month.
And you say at the top that the WIMP and the super WIMP have similar masses. So I guess I'm wondering how we're getting hot dark matter from this. I mean, if I have my WIMP decaying into a super WIMP, wouldn't it be moving at approximately the same speed as my WIMP?
So here it's just a confusion of maybe misusing the word similar for too many things. Similar here means of order the same magnitude. So like, like I mentioned, 300 GeV for the WIMP, 100 GeV for the super WIMP, not hierarchically separated. And so, if you have a 300 GeV particle decay to a 100 GeV particle, that 100 GeV particle is still going, 0.1 C or something like that. It is a significant velocity relative to the WIMP, which, as I mentioned, was effectively at rest at that time. But yeah, if it was, 100 GeV and 99.9 GeV, then that won't work.
Go ahead.
Sorry, you're muted, Jonathan. Could you say a little bit more, please, about how super WIMPs could solve the lithium problem?
Okay. So this is some work now fairly old by Feng, Jadanzik, and Motaka. And basically what you have to do is you have like all the light elements abundances established through BBN at a second. And then along comes this decay, like in this case, maybe say 1,000 seconds later. And all of a sudden the universe, all the dark matter, every single dark matter particle in the universe is now shooting out photons with some 100 GeV energy and into the universe. And so this can break up the light elements, right? So there's then a complicated web of nuclear processes you have to trace through. So, it can break up deuterium because, well, first of all, the photons go into this plasma of the universe, and they, they degrade and they turn into like electromagnetic jets. So now you've got like electrons and photons spraying out, and then they hit things. And so if they hit deuterium, maybe they break that deuterium apart because deuterium is very weakly bound. Helium-4, they don't break apart as much because it's more tightly bound. And lithium-7, they break apart, and so that reduces lithium-7. Maybe some other thing breaks and turns into lithium-7, so you make lithium-7. I don't know, there's just a whole variety of stuff that goes on. But basically, there are these world experts in BBN who basically take standard BBN and put in this source of photons and then see what comes out. And the point is that at certain times for the decay and certain energies of the decay, you can actually rectify the lithium-7 without messing up any of the other observations. And so then it's a solution outside of the standard BBN framework, but it's a solution to the lithium problem.
Interesting, thank you.
Yeah. Sorry, Alessandro.
No.
Yeah. Go ahead.
Could one imagine this WIMP to super WIMP decay to happen much later in the story of the universe, such that today dark matter would be made both of WIMPs and super WIMPs?
So I only heard clearly the last part, which was, can it be that the universe is made of WIMPs and super WIMPs? And yes, I think that's true. Well, it's an interesting question. If the lifetime were made to be, 10 billion years, then certainly in terms of this plot, then you could be at a time where the WIMP and super WIMP abundances are similar. I guess the question then would be, if you made the lifetime so long, you will have then WIMPs decaying to super WIMPs, throughout the history, including 5 billion years ago, including 100 million years ago, and maybe that violates some constraint. So one would want to check that. But in terms of just relic abundance, you're absolutely right. You could have a sort of a borderline scenario where you haven't completed this transition yet and you're stuck with half of each. That'd be very interesting, actually. Thank you.
Okay, yeah.
If I understood things correctly here, the dominant scale for dark matter production is the mass of the WIMP, right? So if it's the order of the superWIMP, then you can use the word dark matter thing to put constraint on the mass of the next to lightest particle, right? And if so, what's the constraint on that? Because it's a constraint on supersymmetry, I think.
Yeah, okay, that's interesting. So the idea is that, if I understand the question right, that we're making the super WIMPs, which could be warm, but for some parameters they could also be hot, and of course that's excluded. It can't be too hot. So what parameters of the theory give that? I'd have to go back and look. I think we did do that, and certainly in this paper, Manoj Kaplan had in 2005 did do that. So I don't remember the numerical answer, but you're definitely right. There is some constraint, and probably there's some constraint on how big that splitting can be, because the bigger the splitting, the faster that super WIMP goes and the more hot it is. So if you fix the super WIMP mass, then there's an upper bound on the WIMP mass because you don't want that splitting to be too big. But that's a great question. I just don't remember the numerical answer. But I'd encourage you to go look at this paper. It's a pretty cool paper too.
Other questions? Yeah.
Yeah, so since these super WIMPs are produced with like these large velocities, if I understood well, you cannot form like these small scale structures. And so my question is, these small scale structures would be something like sub-halos, and if that is the case, how can we reconcile that with observation? Can we?
Okay, so this is this giant area of the question of whether cold dark matter reproduces what we see on small scales. And so what you want to do is not destroy the successes of cold dark matter, namely this formation of galaxies and galactic halos on large scales. But what you want to do is just, in some sense, slightly suppress on very small scales. So, the simplest and maybe the oldest form of the problem was this cuspy halo idea, which is that if you go way into the center of the galaxy, you, in cold dark matter, see a very pronounced increase in the density. And so it's kind of being thought of as a spike. Whereas it seems possible, given measurements of, rotation curves and things of galaxies, that what's actually seen is not a spike, but what's called a core. And so that's one version of the possible discrepancy between cold dark matter and halo profiles. There's other ones, just the number of little subhalos that are around. So, I guess this really belongs in Anne's lectures, and I'm not sure if she's covered it yet, but the general point is that you want to destroy structures on small scales, but not everything, right? And so there's some correct region of every single warm dark matter model where things are not too cold, not too hot, so they're allowed, they're consistent with galaxies, but they maybe resolve some of these smaller issues which have to do with more detailed questions of halo profiles, core versus cusps, and things like that. So you don't want to drastically change things, because cold dark matter does a really good job, but there are some indications that you might want to slightly change things.
Okay, then.
I thought I saw another hand, but maybe not. There's nothing in the chat either, so yeah, please go on, Jonathan.
Okay, so given the time, maybe I'll skip this. What do we have there? Well, okay, this is just too fun of an idea to skip. So let me just tell you this. One thing I did mention is what are the implications of super WIMPs or colliders? And we thought about this, and basically you could have a scenario where you have a STAU, say, produced at a collider, and then it decays to the gravitino, but after a month. Okay, it's very natural that this month scale arises. What that means as a collider is you could potentially make a STAU. And what is a STAU? A STAU is a, electrically charged 100, well, maybe 500 GeV particle or something like that. And so you're making this very heavy, it's kind of like an extremely heavy muon, okay, which will go through your detector and then, just keep going. It doesn't stop, or typically doesn't stop, and it doesn't decay, so it just keeps going. And so you see these extremely weird events with heavy charged particles that don't decay. And so this is a weird exotic signal at a collider. Eventually, of course, these things can be stopped because they're charged. So they do things like they lose energy through ionization in matter. And so they'll slow down and eventually they'll stop. And so one could conceivably do the following thing where, maybe at the next time the LHC turns on, you see that they're making these heavy charged particles. That's already the discovery of something beyond the standard model. But then you could say, well, they're heavy charged particles, they're going to decay. Let's put like a big water tank at the bottom of Atlas, and some of them we can catch in there. And then since there's water, we'll drain it into some truck and drive the truck down to Gran Sasso and then watch the particle decay a month later. And this was actually an idea put forward with a graduate student of mine, Brian Smith. And if you think that's crazy, there were even crazier things. Hamaguchi et al. Said, okay, here's what we do. We make the STAUs, we see these things go through. Some of them will actually get stuck in the LHC. So then we turn off the LHC and we quiet down the detector, and then we surround, but we still look for these things. And then, a month later, out pops this bizarre anomalous event where this STAU, which was stuck in, say, the hadronic calorimeter, decays, and you see this weird signal come out. And then DeRoque et al., including the current Director General of CERN, said, here's another idea. Some of these leptons are going to come out of the detector, but they'll get stuck in the detector hall walls in the rock. And with very precise tracking and measuring the energies, we could tell how deep into the wall they got stuck. And we can then dig out little chunks of dirt from the wall. And we know that there's a lepton in there, and then look for it to decay later. So anyway, this is like, in the realm of crazy ideas that can emerge from slight variations in the WIMP miracle story. All right, given the time, let me move on. So the last one I want to discuss is WIMP-less dark matter. And this really is a nice transition into the whole other realm of dark matter model building, which is hidden dark matter, dark sectors, dark photons, secluded dark matter. There's a whole range of words for this, but it's basically, light dark matter, which has been an active area for the last 8-10 years. And so I wanted to sort of transition to that. And then you'll hear, no doubt, great lectures from other lecturers about this in the coming weeks in this school. So, okay, this particular incarnation I'm going to talk about is very, very much connected to the WIMP miracle, but there are others which are more detached but give the same phenomenology. Jason Kumar and I wrote this up in 2008. So recall the WIMP miracle. For you guys, this is, I don't have to say this for the nth time, but here it is. When you freeze out, the cross-section determines the amount left over, and the cross-section has some form, g to the 4th over m squared, because of diagrams like this. You plug in the correct coupling, the weak coupling, you plug in the weak scale, mass, and out comes the right reluctancy. Okay. An obvious thing, which is obvious to everybody who studied this long, long ago, is that this equation, if you know omega x, does not constrain the coupling and the mass. It constrains the combination here, right? And so if you had a theory where the G could be smaller, you could have smaller masses and still get the same reluctancy. Or if you had series where the coupling was much stronger and larger masses, you could get the same reluctancy. So you constrain a combination, but not either one of these. Now, that observation lay just sort of sitting there for a long time because, you know, in the standard model, we only have one possible coupling here. If you're going to use a standard model gauge interaction, it's got to be the weak one, and the weak one is 0.6, and so that's this whole miracle. Okay. But you could consider like new gauge interactions. And so this is this whole story of hidden sectors. So suppose you had the standard model, but in addition, you had a hidden sector, by which we mean a sector that has dark matter in it, but also other stuff, like other matter, possibly. In inelastic dark matter, we already saw a two-state dark matter system, so okay, that's okay. But also a maybe more forces, like a dark electromagnetism over there, okay? What would then happen? Well, you could get dark matter over there, which has a gauge interaction with a coupling that's, you know, 0.01 instead of 0.6. And the mass of the dark matter over there could be suitably scaled down to preserve this ratio. And you would have the same WIMP miracle story in that hidden sector as we have in our sector. But you wouldn't have any WIMP particles, okay? Now, Jason and I actually went way beyond that and constructed models where this sort of behavior flows out naturally. And in fact, it happens automatically in some models that were studied for other reasons. So these are these gauge-mediated supersymmetry breaking models, anomaly-mediated supersymmetry breaking. To make a long story short, in these models, for various reasons, the mass of the superpartners is proportional to the gauge coupling squared. Okay, and so in the supersymmetric standard model, you got leptons and squarks, which got masses that were proportional to the gauge coupling here squared. So if they were squarks, they had heavy masses because they had a strong coupling here. If they were SU2 left leptons, they had slightly lower masses. And if they were just U1, you know, lepton right or something, they would have just smaller masses because the gauge coupling was smaller. This is a very standard story that was explored in thousands of papers. What happens if you add a hidden sector on here? Well, because of the way the supersymmetry breaking happens, you get the same relation over here, just with the hidden sectors gauge couplings. So we'll call that G sub X. But the same thing happens. The mass over here has the mass proportional to the gauge coupling squared. And so the point is that you have exactly the same scaling that's required to keep this ratio fixed. And so you had these very well-known scenarios, gauge mediated or non-mediated supersymmetry breaking. All you had to do is tack on hidden sectors, and you find that these hidden sectors all have the exact same sort of moral imperative to have dark matter with the right reluctancy. Okay. And so what happens then? You know, what are the implications of this sort of thing? Well, so basically what you have is what we call the wimpless miracle. You have a theory which has the same reasons to have the right relic density, dark matter, but you don't have a single WIMP in the entire theory. You don't have 100 GeV particle interacting through the SU2 interactions, okay? So here's a plot that illustrates this in gory detail where you actually calculate the freeze out and do things with the Boltzmann equation correctly here's the mass of this particle in the hidden sector. Here's the coupling of that hidden sector. And basically, these lines are showing you the region with the right Rayleigh density. And it's exactly what you'd expect. You would find that, for lower masses, you can get lower couplings. But, you could have, in this case, a 1 GeV dark matter particle with a 10 to the minus 2 coupling, or, even lighter MeV dark matter down here with slightly smaller gauge couplings. And so this opens up, an entirely new brand of dark matter phenomenology in models where you have exactly the same WIMP-less WIMP miracle going on, but totally different phenomenology. So what is the phenomenology? Well, this is one of the growth fields in the field for the last decade. So it's hard to summarize, but just quickly, what you're predicting then is sub-GeV dark matter. And so, little experiments that don't have to be at the energy frontier can now probe these scenarios. So we're talking about long-lived particles or light, very weakly interacting particles, feebly interacting particles. There's a whole bunch of names for them. They're all the same thing. So that's on the particle physics side. It's spawned a whole bunch of interesting new particle experiments. On the astrophysics side, it's now opened up this idea that you might have dark matter that has its own interactions. So basically, you could have self-interacting dark matter. And we're envisioning a dark matter setup where dark matter has its own electromagnetism. So dark matter might be, basically dark electrons that are Rutherford scattering, just like basic QED, but in the dark sector. And so, here's an example. So dark matter might repel dark matter through the exchange of some, fifth force gauge boson, okay? And that's interesting, but it might even be really interesting because of the same issue of small scale structure. So there are some indications, as we talked about, that dark matter might be less cuspy. One way to do that is to make it warm. Another way to do that is to make it strongly self-interactive. So basically, when it wants to gravitationally contract into very sharp densities at the core of galaxies, these strong self-interactions basically knock them out. And so it sort of softens the buildup of density in the core of a galaxy. And so there's a beautiful review by Jul29 and Haibo Yu, where they talk about this sort of thing. And here's a typical kind of plot. Here's cold dark matter. What is this? This is the distance from the center of the galaxy. And this is cold dark matter, which is going to very high densities at the center. But if you have self-interacting dark matter, you can basically soften that so it's sort of more flat here instead of spiking up to very high densities. Okay, so what's interesting about that is that you might solve an astrophysical problem. You do need a particular self-interacting cross-section, and that is a centimeter squared per gram for astrophysicists, barn per GeV for particle physicists. But basically, if you had dark matter that was like 100 GeV interacting through some gauge boson with 100 MeV, interacting through 100 MeV mass, you could get big enough self-interactions to resolve these problems. And so, this might be taken as indication that, in fact, yes, there is a hidden sector with the dark matter in it, and the scale is actually 100 MeV, not 100 GeV. And with the WIMP-less framework, you have exactly the same motivations in terms of the miracle. So here, this is my last plot. This is what I'm saying here. If you talk about the thermal relic landscape, you have some mass of the dark matter, or the dark sector, some interaction strength, okay? From purely particle physics point of view, particle colliders basically shine a light on this plane from up here. And so like a particle like the electron, which is an MeV in mass and has an order 1 coupling, is very easy to find. And of course, we found that in 1895. Then we found muons and strange quarks, etc., all the way up here. And we've kind of gone out from there. You can go toward heavier masses. You can go toward weaker interaction strengths. Down here, there's some region where it's just impossible. You'll never discover, at a collider at least, a TV particle that interacts with 10 to the minus 6 couplings. Okay, so this is impossible, but up here is possible. And then here is the region where we might be able to find new particles in the coming years, which is on the border, on this diagonal. What I'm saying with this WIMP plus miracle story is that there's this incredible, interesting synergy between that particle physics story and the relic density, because here's like an example where dark matter freezes out by annihilating through a dark photon to electrons. Okay, it's got some form like this. The point is, though, that in this story, all the particles up here interact too strongly, annihilate too strongly to be the dark matter. There's just too much of it. Or sorry, too little of it. They annihilate too efficiently, so there's not enough dark matter left. Down here, there's too much to be dark matter because the annihilations are too weak. And right along this diagonal is a region where you have the just right amount to be dark matter. This point up here, interaction strengths of order 1 in TeV, 100 GeV scales, the fact that this is at the border of what we can find in particle physics and simultaneously at the border of what's exactly the right relic density, that's the WIMP miracle, okay? The fact that those two particle physics and cosmology considerations overlap, that's the WIMP miracle, that's this. But the point is, they don't overlap actually at a point. They overlap in a line in this plane, which goes down this diagonal. All the particles along this diagonal have the right thermal relic density. And coincidentally, this line has a slope such that basically you're also right along the border of what can be discovered in particle physics experiments. And so, for decades, we were just really focused in on the WIMPs up here. But in the last several years, people have realized that same motivation can basically be applied to thinking about all sorts of things down here as well. And it's led to really a boom in the activity in the field. Okay, so let me just finish with the summary and then we'll come back for questions. So here's the summary, the 4 different sections I talked about. Why WIMPs? So, the WIMP miracle and the discrete WIMP miracle imply that WIMPs emerged very naturally in a whole bunch of theories as stable, cold, collisionless dark matter particles with the correct relic density. WIMPs in symmetry, supersymmetry, I talked a bit about those. They sort of are particularly interesting regions of parameter space. WIMP detection, all sorts of good ways to look for these things. And then finally, this lecture, WIMP creations. The bottom line is that with little tweaks, you can keep the WIMP miracle, but get very different effects, which motivate, different collider searches, different direct detection targets, have effects in the early universe, BBN, CMB, and maybe most interesting these days may have small scale structure implications. So people, astrophysicists who can very precisely think about the universe on small scales have a lot to say about particle physics properties of dark matter. And so that's an interesting field right now. Okay, so let me take questions if there are any about this last topic or basically the entire lecture series.
Thank you, Jonathan. Questions here?
I have a question going back to the conversation about the gravitino from earlier today.
Okay.
You said that the usual assumption is that the gravitino is not the LSP. Why is that a good assumption to make?
So the answer is it's not a good assumption to make. It just isn't. So in particular theories like anomaly mediation, the gravitinos appear more toward the PeV end of the scale. Okay, in those theories, then it's not the LSP. In other ones, gauge mediation, it's down here at the sort of KeV scale, and it's always the LSP. And gravity mediation, it's sort of hanging around the same scale, and whether it's heavier than the lightest one or not is sort of 50-50 sort of proposition. And so, yeah, the point is that this assumption, which is in, the bulk of the literature, is just not a correct assumption. I mean, you have to assume something, so fine, go ahead and assume one. But the point is that most people assume it without even knowing they're assuming it. And there is a whole different half of the parameter space where the gravitino is the lightest.
Thank you.
Next. Yeah, Max.
I guess maybe might it be the normal assumption? Because if we're saying my gravitino has to have weak couplings, that might give it a small mass, right?
So no, that's not right. So
if it gets its mass through the Higgs mechanism, right?
okay, yeah. So if it did, then your reasoning would be right. But the gravitino doesn't get its mass through the Higgs mechanism. It gets its mass through supersymmetry breaking. So basically, if there wasn't supersymmetry breaking, the gravitino would be degenerate with a graviton, which is massless, and so it'd be totally massless. And then there is supersymmetry breaking, so then it breaks at degeneracy and it lifts the gravitino mass. And exactly what it lifts it to, that's the question. And that has to do with the scale of supersymmetry breaking, which is not exactly determined by the scale of where the superpartners are. And so that's what leads to this EV to PV range here. And so it's actually, it's got a, in short, the gravitino has a mass generation that's different from all other particles, even superpartners. And so where it lies is sort of a model dependent question.
Yes.
I had a question about SUSY and grand unification that we partially discussed yesterday. So you said that grand unification in SUSY reintroduces proton decay. Is this because we have so the standard model, then supersymmetric particles, and then some additional particles for grand unification?
Yes, very good. So, and again, I'm sorry, number one, that I couldn't talk for 15 hours, and number two, that I'm not there to discuss this over dinner with you, right? This would be much better. But what you say is exactly right. When you have a picture like this with grand unification, the couplings all meet here. That's a great success. But that means that the symmetry, the grand unified symmetry, broke at this scale. And just like the breaking that we're more familiar with, where electroweak symmetry breaks into electromagnetism and weak. When you do that, you get new particles, right? So the W and the Z have some mass of order the scale at which that breaks. Same thing happens here. You have some grand unified theory, which has a whole bunch of gauge bosons that mediate interactions. In the case of SU5, you have 24. And then you break, and down here, there are a bunch of gauge bosons like the photon, the Z, the W, the gluons. And if you count them up, that's not 24. So where did the rest of those degrees of freedom go? Well, the answer is there are extra gauge bosons that have mass at the breaking scale, which are up here. And of course, if it's a Higgs mechanism, you've also got a bunch of sort of grand unified Higgs bosons that are also a mass up here. And so there's extra particles that have to come in, and those particles are the ones that mediate proton decay, not at the super fast level that we discussed for our parity violation, but fast enough that, if those masses were like 10 to the 14 GeV, you would have predicted proton decay with, lifetimes of 10 to the 28 years, and that violates current bounds by 6 orders of magnitude. So that's completely not viable anymore. And so they have to be up here. But, this is a possibility. And there are SUSY gut theories that predict proton decay right beyond experimental bound. And so experiments like Hyper K or Dune, which are neutrino experiments, are also proton decay experiments. And so anything that's going to push back the limits on proton decay, and maybe see proton decay, are probes of SUSY grand unified theories. Does that answer the question?
Other questions? Last chance. All right. Jonathan, I think there are no more questions. I think also in the chat there's nothing more. So all that's left is just thank you for the great lectures.
Thank you. Okay, thank you, Yuri, and thank you all you. And again, apologies for not being there, but I wish you a fantastic next 3 weeks.